All right, so this is the notes for the next section on looking at transformations. Last day was translations, which is where a function remains congruent, which means the shape doesn't change. It just slides around, up, down, left, right. Now we'll look at reflections and stretches, where the shape is no longer congruent necessarily. And again, all of these things connect back to what we did with quadratics. A little bit more complex, but like before, the more you understood this from quadratics, the easier this gets. That said, again, I start with this absolute value function, g of x. And I can tell it's an absolute value function by looking at it. It's kind of a distinct look, that sort of point there. And so the first thing I say is determine the equation of g of x. Again, it's good to remember that g of x is the absolute value of x. Remember, absolute value brackets are brackets. They're parentheses. They affect the order of operation. Just whatever's inside them, the sum, the total of what's inside them is positive. All right. However, I just realized I made a mistake, because this would be the absolute value of x if this point right here was at the origin, but it's not. Right? If that point was right here, then that's the absolute value of x. But if I look at this a bit more carefully, that what I gave you is the exact same as the absolute value of x, but translated 4 units to the right. So if I want to translate any function 4 units to the right, I want to subtract 4 from the input. So actually, this should be the absolute value of x take away 4. There we go. OK. With that said, for each of these below, I want to just make a sketch as well as state what the transformations are. So let's look at these one at a time. The first one, instead of g of x, and remember, g of x this time represents what's graphed and represents, I've now found the equation, the absolute value of x take away 4. So again, that's what's g of x. It's given up there. Or maybe I'll just label that. So this is y equals g of x. All right. Everything we're doing is based on that. Remember, none of these 3 equations down here can be graphed unless we refer back to what g of x represents. However, even if I don't know what g of x is, I know the transformations being applied to g of x by just looking at this. For example, in the first one, that 2 in front of the g of x, that means I'm multiplying the entire function by 2. All the outputs are being multiplied by 2. And that is what we call a vertical expansion by a scale factor of 2. And I'm just going to put SF for scale factor. Quite simply, the coefficient in front of the entire function is the scale factor. And remember, this phrase we saw with quadratics, this means all my y coordinates are going to be, in this case, doubled, times by 2. My x coordinates will remain unchanged. So what does that look like? Well, let's look back here. I can pick any points I want. I'm going to start with that point I've already drawn a dot at, the sort of vertex of this. And I'm going to leave all the x coordinates alone, but the y coordinates will be doubled. And maybe I'll draw this in red. And so this point will remain the same. We call that invariant. It didn't change. That particular point stayed the same both on g of x or when I have 2g of x. However, all the other points will change. For example, this point right here has a y coordinate of 1. Well, now I'm going to double that. So that y coordinate will now be 2. And this is symmetrical, so I can just plot that other point right away. At this point, I can visualize this graph pretty well, but why not pick one more point? This point right here, that point right there, has a y coordinate, an output of 2. I want to double it, because the scale factor is 2 times by 2, which is 4. And again, I can just copy it over here, because it's symmetrical. At that point, I have more than enough to visualize this graph, so I'm going to grab a ruler and not only draw it, but label it. So this is the equation for 2 times g of x, or 2g of x. All right. As well, down here, I ask for the actual equation. So the actual equation of this is just 2 times the absolute value of x. Because again, the absolute value of x, absolute value of x, take away 4. Keep forgetting that. Bad teacher. There we go. Because again, for this particular question, g of x is, as an equation, the absolute value of x take away 4. All that, everything that's highlighted in yellow is equivalent, is g of x. All right, so let's look at the next one. I have a 1/2 in the front. Well, that 1/2 represents a vertical compression, we say. Although If you want, you can use the word stretch for either expansion or compression. Stretch kind of covers both. The most important thing is the scale factor, and that's vertical. So a vertical compression or a vertical stretch by a scale factor of 1/2. Because again, I'm multiplying by 1/2. And we saw this quadratics. That means all my outputs will be multiplied by 1/2. Multiplying by 1/2, same as dividing by 2. And so let's draw this in purple. And so those same points, oh, that's not purple. I'm going to use the same points I started with. So again, this sort of vertex has an output of 0. 0 divided by 2 is 0. That doesn't change. This next point has an output of 1. But divide by 2, it's now 1/2. So I know it's going to go through that point. And this next point over has an output of 2. Divide by 2, or multiply by 1/2, output of 1. And it's symmetrical. So I can quickly visualize what 1/2 g of x looks like. That's a bit messy. Let's try that again. And so what I've just sketched is 1/2 g of x. And again, g of x is what we started with. In this case, it's the absolute value of x take away 4 if we write it as an equation. And so if I want to write 1/2 g of x as an equation, it would be y equals 1/2 times the absolute value of x take away 4. Because again, that 1/2 is clearly in front of g of x, so it should be clearly in front, not inside, the absolute value of x minus 4. All right, so last one. Maybe I'll focus on just the writings first. So here I have a -3 in front of the g of x. So the negative tells me something, and the 3 tells me something. Let's do this in orange. So the negative tells me there is a vertical reflection. However, there's more. The 3 tells me there's also a vertical stretch, or I'm going to be a little more specific and say vertical expansion. Although what I really care about is that it's vertical and that there's a scale factor by a scale factor of 3. Now notice I didn't say the scale factor was -3 because the negative told me it was reflected. The 3 is the expansion. So the equation for this would be y equals -3 times the absolute value of x take away 4. And so what does that look like? Well, compared to what I started with, I'm going to reflect it vertically and I'm going to stretch it. I can perform these two transformations in any order. It'll look the same in this case. But I'll start with what I think is the simplest. And again, I'm always going back to g of x, which is the dashed blue graph. I'm going to reflect that upside down first. And so that stays invariant, but then all these points are below. But I'll draw this just lightly, because I'm not done yet. That's just the reflection on g of x. Now I need to stretch it by a scale factor of 3, which means the y coordinates, the outputs of all those points I drew, are going to be 3 times more. And so still goes through that same point, but all the other points will change. So instead this point here, instead of being at -1 on the y, it's going to be at -3. This point here, instead of being at -2 on the y, it's going to be at -6. So kind of down here. And then I can just reflect these because my shape is symmetrical. And so this, even though it's going off my grid a little bit, is my sketch of what -3 g of x looks like. Or, if I want to write the full equation, -3 times the absolute value of x take away 4. All right. Before I go on, let me show this, an example similar to this in Desmos. So what I have here, I wouldn't really worry about the equations at the top of the screen here. What I have here is a graph in blue that I'm calling f of x. What I have here in green now is the exact same thing, because I'm transforming it, but I am multiplying the whole thing by a, but a is 1 right now. So multiply by 1, nothing changes. And so right now, my original function and my transform function are identical. I want to make a bigger. Right now, a is 1. And remember, if you look at the equation for what's in green, a is the coefficient in front of f. The b value I'm going to talk about in just a moment. And so if I start to make a larger, I'm multiplying by numbers larger than 1, and it gets stretched vertically. If I go all the way up to 5, for example, all the outputs, all the y coordinates on that blue wave are now being multiplied by 5. And so notice the highest point it gets to is 5 times higher than before, up at 15. Whereas notice all the x-intercepts are the same. between these two functions, because the x-intercepts are where your outputs are 0. 0 times anything is 0. And if I make a number between 0 and 1, let's say let's go with a half, all my outputs are 1/2 of what they used to be, although the x-coordinates are again the same. And if I make a negative, it starts to reflect vertically and then keep getting stretched more and more and more. Get the -5. Again, the x-intercepts haven't changed the entire time. The x-intercepts have been invariant because all the outputs there are 0, but every other point has, in this case, been reflected vertically and stretched by a scale factor of 5. So all of that I'm not saying is easy, but will probably be easier than what we're about to do, because all of that connects directly back to what we saw with quadratics. What you didn't do with quadratics, most likely, is see what happens if you multiply the x by a number, the input by a number. All right? So let's look at that. OK, what I have here is the same original function, which for some reason doesn't want to load up properly. Give me 1 second here. Why is this not working? There we go. Let's see if that fixes it. Perfect. All right. So again, same g of x. Looks like that song I sung worked. So I'll label this as g of x. And don't forget again, g of x is the absolute value of x take away 4. Take away 4 inside the absolute value. All right. So what happens if I multiply the input by 2? If I look at this example right here, what happens if I multiply g of x by 2? So just the x by 2, not the whole thing. Well, first of all, maybe I'll write the equation. OK, not this will help too much maybe, but the equation would be y equals the absolute value of 2x take away 4. Wrong type of bracket. There we go. Right, because g of x itself, and maybe I'll remind us of that right here, g of x is the absolute value of x take away 4. And the only difference between that and what I have down here is that instead of x, it's 2x. So in my equation, instead of being x minus 4, it's 2x minus 4. So that's the equation. So what difference does that make? Well, what that's actually going to make is a difference of a horizontal compression. So let me write down the words and then show you what it's going to look like. OK, so we call this a horizontal compression by a scale factor of 1/2, not 2. It's the reciprocal. And what that means actually is that all my x-coordinates are going to be cut in half. They're going to be divided by 2 or multiplied by 1/2. So let me show you what it looks like, and then I'll go back to Desmos in a second before I look at the others. OK, so this is not something you saw with quadratics. But if I go back up here, first let me just kind of show you what that means. A horizontal compression by a scale factor of 1/2. Well, I'm going to pick a point. Start with this point again. This time my y-coordinates are going to be unchanged because it's a horizontal change. But my x-coordinates are going to be multiplied by 1/2, the reciprocal of the 2, or just divide by 2. And so in this case, I'm going to draw this in red. And so instead of that point being at 4, 0, it's going to be at 2, 0. And I can do the same thing for any point. So this point here, which is 5 over to the right, is now going to be 2.5 over to the right. This point right here, instead of being 6 over to the right, is going to be half of that. It's going to be 3 to the right. And now I got to be careful because my shape will be symmetrical, but not, I don't want to jump to a conclusion too quickly. And again, all I'm really doing is picking y-coordinates and dividing by 2. So let's take this point right here. That point is 3 to the right. Half of 3 is 1.5, so that's going to be right here. And let me pick one more point. So that point I just drew is 2 to the right of the, and I say 2 to the right of the, I'm looking at the y-axis. So now it's going to be half of that, so 1. So I've just drawn 5 points now. I can kind of get the idea that it's going to keep looking like this. If I don't have that sense yet, well, then just pick more points on your original graph. But I got it more than enough to visualize this. So this is what a horizontal compression by a scale factor of 1/2 looks like for this particular function. So this is the graph of y equals g of 2x. And you never really saw this with quadratics, so I wouldn't be surprised if you thought it would be the other way around, if you thought the x-coordinates would double instead of half. And so if I just switch back to Desmos for a second, this time I want to focus on the b value. So right now b is 1, and notice if you look at the equation for what is in green, it's a, but I'm going to leave a at 1, times f of b times x. And so when b gets larger, I'm going to bring b up to 2. Notice it gets compressed. All my x coordinates are being shrunk. All my x coordinates in this case are being divided by 2, or divided by 3, or divided by 5. If you look at this graph, the difference between the graph in green and the graph in blue is that every x coordinate has been divided by 5. Because multiplying by 1/5 is the same as dividing by 5. And so let me just put this back to 1 for a moment and go back to here. All right, so for this one, I have not a 2 inside, I have 1/2. And so perhaps you can guess that this is going to be a horizontal expansion by a scale factor of not 1/2, the reciprocal of a half, which is 2. And chances are this is what you would have guessed for the previous one. And so the equation for this is y equals the absolute value of 1/2 x. Take away 4, that's the equation. But what does this look like? Well, all my x coordinates are being expanded now. And again, it's the exact same idea as we saw with vertical stretches, just we got to remember the scale factor ends up being the reciprocal of what we see in the equation. And that may throw you off for quite a while. Hopefully not too long, because this is like the foundation of the course, but I would not be surprised if that throws you off a bit. When it's a horizontal stretch, the scale factor is the reciprocal of the value you see being multiplied to x. When it's a vertical stretch, it's the exact same, so that's why it's simpler. And so if I look up here, a scale factor, a horizontal expansion by a scale factor of 2, I'm going to start with these same 5 points I've looked at in blue here, except I'm going to double the x coordinates. So this point right here, instead of being at 4, it's going to be at 8. And this point right here, instead of being at 5, it's going to be at 10. So already, I can't really show that so well on here. I can estimate about roughly right here. So I'm going to then look at this point right here. Instead of being at 3 on the x, I'm going to double. It's going to be at 6. And I can kind of see what's happening here, but I'll pick one more point. Oops. And so this point right here has an x coordinate of 2. I'm going to double it. It's now at 4. And so I have enough, if I connect the dots, to kind of visualize this quite accurately. And so compared to the original function, this is what a horizontal expansion by a scale factor of 2 looks like. Or this is what the equation of g of 1/2 x looks like. All right, so lastly, minus 4x. Two things are happening here. And so perhaps you can guess that the negative is going to represent a horizontal reflection. When I ask students to guess, they usually guess that correctly. But there's more going on. That's just the negative. The 4 represents a horizontal. Remember, the scale factor is going to be the reciprocal of 4. So the scale factor is going to be a quarter, which is less than 1, which means this is a horizontal compression. But the most important thing is the scale factor, by a scale factor of 1/4. So the negative we see in front of the 4 tells me there's the horizontal reflection. The 4 tells me the scale factor. And so let me write the equation. So the equation is the absolute value of negative 4x, take away 4. But that in itself doesn't do me much good in terms of visualizing this. So if I go up here, I want to take the original function g of x, I want to reflect it horizontally, and then I want to stretch it. I'll do the reflection first. So this point here, instead of being 4 to the right, will be 4 to the left. But then I'm going to compress it by a scale factor of a quarter. So instead of this being at negative 4, it's going to be at negative 1, because I've divided by 4, or multiplied by a quarter. Never forget, multiplying by any number is the same as dividing by its reciprocal. That goes back, way back. But it's an important fact. It's easy to forget. OK, so let me look at this point here now. Let's pick this point here. This point here, I reflect it horizontally. So instead of being 6 to the right, it's 6 to the left. Let's say over here, it's at negative 6. But then I'm going to divide by 4, which is negative 1.5. So about right there. And let me pick one more point. Let me pick this point right here. So that's 2 to the right, so now it's going to be 2 to the left, so it's right here. But then I'm going to divide by 4, so it's 2 divided by 4 is half. And so I have these 4 points. And so what I'm drawing in orange now is the graph for g of negative 4x. That's what the original function g of x looks like if you reflect it horizontally and compress it by a scale factor of 1/4. Chances are that is significantly harder to get your head around than the previous part. And that's really just a sign that you don't look at this with quadratic functions. And if we have time at some point, we'll talk about why. But it's in itself, the only difference is realizing the scale factor is the reciprocal of the number you see being multiplied to x. We usually call it a b value. So let's summarize this like we did last lesson. So for any function, f of x, okay, f of x, all these f of x's represent the same thing. But then there's some negatives in here later on. Okay, for any function f of x, if you put a negative in the front, that represents a vertical reflection. You can also call that a reflection in the x-axis. In mapping notation, it looks like x comma y maps onto the x doesn't change, because you're reflecting it vertically. The y becomes the opposite sign. That's what it looks like in mapping notation. What if you multiply the whole fx by some value a? Well, if the whole function is being multiplied by it, it's always going to be a vertical stretch. Now, whether it's an expansion or compression, I can't tell because I don't know what a is, but I know it's going to be a vertical stretch of some sort. And I do know the scale factor by a scale factor of just a. Whatever a is a scale factor. Hence, it's a bit more straightforward. And so in mapping notation, if I look at some point on my original function, it maps onto the x coordinates won't change. The y coordinates are multiplied by a. So y times a. I'll put in alphabetical order. Say a, y. Again, in mapping notation there, that's telling you what's happening to all the coordinates. All the coordinates, if you have a vertical stretch, by any scale factor, the x coordinates don't change. The y coordinates are multiplied by whatever that a is. So if it's negative, it ends up reflecting as well. All right? And so the points that don't change, the invariant points, I touched upon this. The invariant points are on the x-axis. Again, invariant points, those are the places where, in this case, f of x and the transform version are the exact same. Invariant points are on the x-axis. And we saw that with my example with the wave there earlier. All right, that's nothing that's easy, but it's easier, usually, than if you multiply the x by some value. So if you just make the x negative, again, x representing the input. So maybe I should say a bit more in general. If you make the input negative, if you change the sign of the inputs going in, that becomes a horizontal reflection. Or we can say a reflection on the y-axis.
Ms. Sampson, please call 2226. Ms. Sampson, thank you.
You're welcome. In mapping notation, it looks like x comma y maps onto negative x comma y. Just the x coordinates change. All right. What if you're multiplying what if you're not just changing the sign of x, but you're multiplying by some number as well? There's this coefficient of b. Well, then that's a horizontal stretch. And the important part, as always, is the scale factor by a scale factor of not b, 1 over b, the reciprocal. Really, 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 really important. And so easy to mix up. And chances are you will mix this up a few times at first. Hopefully a few times. We do learn from mistakes, but hopefully we don't just keep forgetting this throughout the course. This will come up. All these ideas form the foundation of this entire course. There is no unit in this course where these ideas don't come back. So the more we can kind of toil with this now and try to get it understood now, the better we'll be off for the rest of the course. In mapping notation, I can express it like this. X comma y maps onto x divided by b comma y. Again, dividing by b, same as multiplying by 1 over b. And the invariant points, you may guess if the invariant points for vertical stretches are on the x-axis, you'd maybe guess that it's going to be for the y-axis, and that is correct. And I'll show you a visual of that in a moment. Invariant points are on the y-axis. So if I just go back to Desmos here in a second, let me show you that part. So again, what you're looking at are two functions on top of each other. I'm going to just make b change on its own. So b is getting, now it's b is negative. So you're seeing b do a whole bunch of things. It's being reflected. It's being stretched, all horizontally. So first notice the y-coordinates are never actually changing in terms of it's never getting higher or lower than that wave you see there. And notice the only point that is staying the same the entire time is that point, in this case, right on the y-axis. And in this case, also on the x-axis. But we also even saw, without looking at this example, if we look at our notes, in the last example, you can see right here. Notice that point right there is the same on both, in fact, in all the graphs. If you draw them fully, all the graphs go through that point. That's on the y-axis. Any sort of horizontal change, points on the y-axis won't change, which makes sense, because any point on the y-axis has an x-coordinate of 0. 0 times anything, it's going to be 0. All right. So let's try using this now to visualize graphs rather quickly. So for all of these, the graph in red is the square root of x. So what would, in this case, 3 times f of negative x look like? And what's the equation? So first, maybe for this one here, the most important thing is to, I think, label the transformations here. So the 3 in front of the whole function, that represents a vertical expansion by a scale factor of 3. Now, if you think of it as vertical stretch, that's totally fine. And to me, the word expansion is a little more specific. What really matters is the scale factor. That negative you see here in front of the x, that is a horizontal reflection. Or you can say a reflection on the y-axis. So I want to perform these two transformations on the graph I have. In this case, it doesn't matter. When all you have are reflections or stretches, the order doesn't really matter. So I'll do it from left to right. I'll do the vertical expansion first. So I'm going to take this, and I'm going to look at these points here, look at these kind of friendly points. Those are the only coordinates I can see that are whole numbers for x and y, and I'm going to triple all the x coordinates. Sorry, the y coordinates. And so this will remain unchanged. This will go up to 3. This will go up to 6. So what I have right here is just the vertical expansion by a scale factor of 3. And notice you can perhaps even see those y coordinates being stretched 3 times higher. OK, that's just the vertical expansion. There's also a horizontal reflection. And so I think that's a bit easier. I can take these 3 points I have in blue and reflect them horizontally, reflect them on the y-axis. And so this point will not change. These will be reflected over here a bit. And now I can draw my curve. So it looks something like that. Oh, wait a minute. Did a little too fast. It should be this point here when I reflect it as 4 over, not 2 over. There we go. That looks better. The good thing about making a graph is if you draw it wrong, there's a good chance if you just pause to look at it, you can just see, like visually, it looks wrong. And what I saw before just looked wrong. There we go. So there's my graph of 3 times f of negative x. So next one. Again, I'll use these same points for this starting function. This time I have, where is it? Negative f of 2x. So the negative, just the negative part, that is a vertical reflection. And just the 2 is a horizontal compression by a scale factor of not 2, the reciprocal of 2, of 1/2. So again, I'll do this in order from left to right, although it doesn't really matter. So the vertical reflection, I think, is the easiest part. So I'm going to take those 3 points, I'm going to reflect them vertically. They now are here. OK, that's just the vertical reflection. And now I want to horizontally compress this by a scale factor of a half, which means those 3 points in blue I drew, I want to take the x coordinates and chop them in half. So instead of being, exactly as they are, well, for example, this starting point will remain unchanged. Half of 0 is still 0. But this next point, instead of being 1 to the right, it's going to be a half to the right. And this point over here, instead of being 4 to the right, it's going to be 2 to the right. And I have 3 points here, so I can now draw this. And I can always pick more points if I want. That's pretty good right there. All right, so last one. This time I got a few more things going on. Let's do this. Let's do this in 2 steps again. So the negative 1/2, in front of the f, that represents 2 things. That represents a vertical reflection. And that's just a negative. The 1/2 represents a vertical compression by a scale factor of 1/2. The negative 2 we see right here. That represents 2 things. It represents a horizontal reflection. And the 2 represents a horizontal stretch, but it's going to be a compression because I know the scale factor is not 2, it's 1/2. It's the reciprocal of 2. And so again, there's 4 transformations here. I can do them in any order. I'm just going to do it kind of boring in the sort of order I wrote them out. So first, the vertical reflection. I think that's pretty straightforward. But I also want to, before I draw too much here, I want to take this and I also now want to vertically compress it by a scale factor of a half, which means these 3 points, I'm going to take the y coordinates and chop them in half. So this point, the origin remains the same, but the other 2 will change. And so the y coordinates I have cut in half. And so what I'm sketching here is just the vertical transformations. That just represents the vertical reflection and the vertical compression by a scale factor of a half. So now, looking at what I have sketched out as a dashed line there, I want to take that and now look at my horizontal transformations. First, I'm going to reflect it horizontally. And so that won't change. And I'm just taking these points and reflecting them on the y-axis. OK, so those 3 points I've drawn, that's just the reflection. And now I want to compress it horizontally by a scale factor of a half, which means those 3 points, I want to take the x coordinates and I want to multiply them by half or divide by 2, which means, again, my function will still start at the origin because the x coordinate was 0. 0 divided by 2 is 0, but the others will change. So this next point, instead of being 1 to the right, will be a half to the right. And this point here, instead of being 4 to the right, will be 2 to the right. So I got a lot of little points going on here, so I got to be really clear about what's what, but this is the curve I'm looking at. Make that a little bit neater. Taking a little while to make this neater. Here we go. Oh no. There we go. Oh no. There we go. My attempts at making it neater have failed. All right, but I should say, anytime we want to visualize the graph by actually sketching it out, our goal is not to recreate what Desmos can do. We'll always lose at that. A computer program, can always recreate an image better than we can. Our goal is to have a sense for what's happening here. And again, you're making a sketch. You're showing you a sort of feeling for things. Remember, computer programs don't have a gut feeling about things. A computer program never kind of gets the point. It never kind of has a sense of what's going on. It just does steps. And so our goal here is not to recreate, like I said, what you create in Desmos. It's to show that you have a sense about what's going on. All right, so the final problem does go into why you don't need to deal with horizontal stretches in Pre-Calc 11. But I will leave this for now, and maybe we'll look at this in class at some point. It's not essential. And again, I've been talking enough, right? So with that said, let me just kind of write down the homework. Remember again, it doesn't really matter how straightforward or not these notes seem to have been for you. You don't really know how well you understand it till you check your understanding by trying these things on your own. And that means also checking the answers. All right? But there's the homework. So thank you very much. And